In this particular related rates problem, we've been given a ladder which is of a fixed length, 5 meters, and this ladder is leaning against a vertical wall. The bottom of the ladder slides away from the wall, and as it does so, the top portion of the ladder slides down the vertical face of the wall. The first thing that we usually do with these sorts of questions is draw ourselves a diagram. Fortunately, a diagram's already been provided in the study guide, but we're going to add a little bit to this diagram. First thing I've noted is that the ladder is of a fixed length, 5 meters, and I've used arrows to indicate which way the sides of our right triangle are changing, or which directions the objects are moving. First of all, as you've noted, I've mentioned that we're dealing with a right angle triangle, so I've written that off on the side. I've put a right angle triangle and labeled the legs of the right angle triangle A and B, and the hypotenuse as C. Now, the only reason I'm doing this is when I start discussing the rates of change and I use the notation for derivatives, I have to clearly define what variables I'm dealing with. Let's start with the hypotenuse, which is C. We've stated that it's a fixed length, 5 meters. Well, that would mean that in this particular rate of change problem, dc dt, the rate of change of the hypotenuse with respect to time, is 0, because the ladder is of a fixed length, there is no change. When we look at leg B of our triangle, that leg of the triangle is indeed changing because the ladder is sliding away from the wall. So dB dt is going to be equal to 0.4 meters per second, and this value was provided in the question. The question asks us to ultimately find the rate of change, or how fast the ladder is sliding down the building. So we're asking ourselves, what's happening to the other leg of the triangle? We want to find dA dt. That's the unknown in this question. So we've clearly made our diagram, identified the variables A, B, and C, and identified the rates of change that have been provided, dc dt and dB dt, and identified which rate of change we would like to find. The next thing we need to do is find an equation that relates those three variables, A, B, and C. Well, we are dealing with a right angle triangle, and you should be aware that the Pythagorean theorem describes the relationship between those three sides. So we write down a squared plus b squared equals c squared. Now the next thing we have to do is do implicit differentiation, and we must differentiate with respect to time. Now if you notice, none of our variables A, B, or C are the variable t, time. Therefore, when we take their derivative, we must use implicit differentiation. If, for example, I was taking the derivative of a squared with respect to a, its derivative would simply be 2a. But since I'm taking its derivative with respect to time, then its derivative will be 2a dA dt. If I was taking the derivative of b squared with respect to b, its derivative would simply be 2b. But again, I'm taking the derivative with respect to time. So its derivative, using implicit differentiation, would be 2b dB dt. And then when I take the derivative of c squared with respect to t, time, I end up with 2c times dc dt. Well, now it's just a matter of filling in the values I know into the equation and solving for the unknown. So on my next line I have 2 times 1.5. 1.5 was the value of a provided in the question, times dA dt, that's our unknown, that's what we're trying to find. Add to that 2 times, well, I need a value for b. So I'm just going to pause for a second and think, how can I go about solving for b? Well, I am dealing with a right angle triangle, And I do know the Pythagorean theorem. I know that a squared plus b squared is equal to c squared. I know that a is 1.5, and I know c, which is of a fixed length, is 5. So I can substitute those two values into my Pythagorean theorem and solve for b. And what I end up with is that b is equal to 4.8. I now can substitute this back into the equation I was working with. So I have 2 times 4.8 times 0.4. That 0.4 was our dB dt provided in the original question. And that's going to be equal to 2 times c, which is 5, times dc dt. And again, dc dt is 0 because our ladder is of a fixed length. It is not changing. Therefore, there's no rate of change of c with respect to t. Or I could say that rate of change is 0. Now, it's simply a matter of rearranging and solving for dA dt. And when I do so, and it takes a few steps, I learn that dA dt is equal to negative 1.28 meters per second. One quick way to check if your answer is roughly in the ballpark is to take a look at the sign. In this case, we end up with a negative. And that's what we would expect because the length of side A is actually shortening as the ladder slides down the wall. So you would expect to get a negative rate of change, and we have in this particular example.